Our next presenter is Jeff Davids. Jeff Davids is passionate about the co-equal goals of providing the food and fiber the world needs while sustainably managing the Earth's limited natural resources. He has worked on these themes in the Western U.S., predominantly California, and in over a dozen countries in Europe, Africa, and Asia. Jeff is a water resources engineer with Davids Engineering, an adjunct professor at Cal State University Chico, the founder and president of Smartphones for Water and H2O Tech, and a water resources consultant for UNFAO. Jeff is a licensed professional engineer in the state of California, has a bachelor's in general engineering from Cal Poly San Luis Obispo, a master's in hydrogeology from Cal State Chico, and a PhD in civil engineering from Delft University of Technology in the Netherlands.
Thank you. All right, well, this is just while we're switching presentations, I just have a quick anecdote, or maybe two quick anecdotes. One is that about 25 years ago, Davids Engineering started a venture called Seaball North America. And there was this Dutch scientist named Wim Bastiansen over in the Netherlands who had estimated consumptive use from the Imperial Valley to within like 1% of the water budget figures. And our minds were being blown by this ability to use satellite data to estimate, crop consumptive use. And really it was too expensive to have a viable business model. It took $20,000 per Landsat scene to process a year's worth of data, basically. And so we did it for a few people who were willing to pay for, a decent amount of money to get those data. It was powerful, but it moved into the research community, and it's so exciting now to be able to access these types of data for free. So isn't it such a neat time to kind of be a water resources engineer and to be able to engage in these things? Okay, so I think let me get the presentation mode here. The last thing, I have to make a public a thank you to Gabriel for CBOP. And so with WIM and the FAO, we've been able to use that data set in Myanmar and Afghanistan, places where they don't have any ground truth data to understand the water budgets. And so thank you for that product, and we'll keep on trying to use that. Okay. We've all seen this picture, probably starting at when we were about 5 years old. And this is about all I understand here about the water cycle. But there was this great publication in the AGU EOS about 4 years ago that highlighted some deficiencies in this understanding that we teach our kids of the water budget. I'm just going to go through those and then add one to the list. So one is, where's the people in our water cycle? Right? Oftentimes water cycles are missing people. We perturb the system in a significant way now. So make sure when you communicate the water cycle to your kids and your kids' classmates, include the people, right? Number two, where's the different biomes? Generally there's these like well-watered things that we see in our water cycle diagrams, but there's deserts and there's, tundra and that sort of thing. So include different biomes. And of course, seasonality, that's a tough one to depict in kind of a static diagram, but think about seasonality. But also, transpiration is not even listed on the water cycle. It just says evaporation. And man, let's get transpiration in there. So I'm going to bring in a slide from the British folks, the Meteorological Association over there. And basically what I want to highlight is that if you really look at the fluxes of water through the landscape, what's interesting is actually about 2/3 of water globally leaves the land surface, not as the water that we see in the rivers, but in this invisible atmospheric river, this slow motion invisible atmospheric river, right, that's moving upwards back to be subsequently precipitated or move on to different places. So this is a big deal, and I think the atmospheric river that's really hot in California, maybe it's all over the West. Everybody's talking about atmospheric rivers, right? But that's only 40,000 cubic kilometers per year. Look at this slow motion, the real atmospheric river here, right? We're all pumped on ET. It's twice that size. So this is a huge flux, and it's very exciting to be able to measure it these days. So basically ETs are planet slow motion atmospheric river. We already talked about that. So basically, I just have two things I want to go over. I'm going to do a very quick kind of flyby of some different ways we're using OpenET, and then drill a little bit farther down into the application to understand wetland ET and kind of the variability across time and space for some wetlands in California. So again, we're just going to go through 4 very simple applications at a pretty high level and then dive a little bit deeper into wetland ET. So the first application is you all probably know that California has experienced some, reasonable droughts of late. 2014-15 was a bad one, and then more recently 2020 through 2022. And OpenET basically gives us a rapid way to communicate the impacts of these droughts on the landscape and the people that inhabit these places. And so what we're looking at here in terms of location is it's the Colusa Subbasin. It's in Northern California in the Sacramento Valley, just kind of to the northwest of Sacramento there. And basically here we have our nice color scheme that we're using to look at these OpenET data, with the yellows representing kind of a low amount of ET, and then the kind of these purple colors, blue purple colors, representing significant amounts of ET. And this is June 2021. So this is when the surface water suppliers in this area, it's predominantly a rice and almond crop composition. Of course, the almonds you can't fallow from one year to the next, but the rice you can. So look at this picture. The rice area is kind of in the middle here. This is, again, June 2021. Surface water suppliers had a good supply of water this year. It wasn't 100%, but I think it was 75%. And then fast forward to June 2022, the third year of this epic drought, surface water suppliers that on paper had a right to no less than 75% of their contracts, they received 18% of their contract in 2022. I mean, so this was a full breach of contract from the federal government for these water users. But look at the impact of this. Huge swaths of land fallowed. And this means jobs, right? This means Pacific Flyway impacts. There's huge impacts to this land fallowing. And this is just a quick way to, again, tell the story to decision makers, tell the story to the scientific community. Just a simple example of using these data to tell these stories. The next one that I want to look at quickly is in the context of SGMA and the Sustainable Groundwater Management Act in California. I think a lot of us are asking the question, is SGMA having its intended effect? Are we seeing reductions in land, in consumptive use off the landscape? And of course, there's the challenges of variability from year to year in terms of effective precipitation. We've heard about that several times already. But these are just a couple examples. And I've just kind of made them anonymous just to keep things easy here. And basically what this represents is an irrigated area analysis using OpenET and kind of a threshold ETAW value that above which we're going to call it kind of a binary classification of irrigated, and below which we're going to say it's not irrigated. And so you can see that in this particular GSA, you do see a reduction on the order of something like 10,000 to 15,000 acres from 2021 through 2023. So it appears that this allocation that's being introduced in this area is actually having its intended effect of a reduced footprint of irrigated agriculture. And then another way to visualize this is across these different zones. You can kind of see across the different years the actual intensity of the evapotranspiration of applied water expressed as a depth. And again, you can see certain areas are actually intensifying while other areas are actually becoming less intense. And of course, this is what we're hoping to do. So then you start scratching your head why is it working in certain areas and not in others? What policies need to be tweaked to make sure that we're having the intended effect across the landscape? Now, of course, if you're a landowner, and I don't know how many growers are represented in this community here, this discussion, but if you're on the other side of this whole scenario, basically where you have a 100-acre ranch, let's say in Fresno or Kern County, and all of a sudden they're saying basically you can only farm about a third of that landscape because when you were farming the whole landscape, we were unsustainably using groundwater. That's a tough sort of pill to swallow, right? It's a very difficult sociological problem. And basically, one of the ways that we're using OpenET and then other ET data sources is basically to build a system to measure and account for consumptive use of groundwater within the context of an allocation. So a lot of subbasins in California for Sigma are saying, you landowner, you get 1.2 feet of water per acre, 1.2 acre feet per acre of water. You can choose what you want to do with that water, but when that's gone, you're going to pay a penalty if you use 1.3 acre feet per acre. If you use 1.5, there's going to be a penalty on the order of hundreds of dollars per acre foot. And so they need to believe that the data that they're seeing, the measurement of that ETAW is correct. And so we're doing a lot of work where we're comparing here on this plot. We have time. This is from 2023. And then this is actually the volume of water expressed in acre feet. And then over this landscape, which is about 20,000 acres, what we're looking at basically are 4 different measurement methodologies with flow meters. So we actually have applied water data for all 40,000 acres of these lands shown in the blue. And then we have 3 different measurement methodologies, and one of them is OpenET. That's this kind of red dotted line. And so you see that there's very nice agreement, both in terms of magnitude and also in terms of the shape of the curve, between the applied groundwater measurement that's on average about 2.1 or so acre feet per acre, and then the OpenET, which is something less than that. And Gabriel already touched on this, that difference basically is the consumptive use fraction. So if every 100 drops of water you apply to the landscape, there's only a portion of those drops that actually ends up being consumptively used, and that's on the order of maybe around 0.7 to 0.8 to 0.9, depending on your irrigation system and your soil type and that sort of thing. This is just an example of a communication of these data to the growers. So here we have a percent of the allocation remaining, and so you have like the allocation used in blue kind of going up to 90, in this case, 97.5% or so, and then the part remaining. Here's the kind of the red line, don't go over that. If the blue goes over that, you're going to be in penalty, and then some communication of that allocation remaining, some information about the grower here. And we're actually transmitting these to, literally hundreds of growers across the landscape to try to implement these allocations. All right, I'm going to need to go faster because I want to talk about wetlands a little bit here, so I'm keeping an eye on time though. Okay, all right. This is, I think, the second to last kind of little example of how we're using OpenET before the wetland stuff. This is basically a domain of a groundwater model. It's an IWFM model built by the DWR. It's an integrated surface water groundwater model. And the kind of the historical approach of getting the ET forcing, for these models is basically to understand the landscape in terms of its land use, and then to get reference ETs, and then to get crop coefficients for these different land uses, and then to compute, with the FAO 56 approach, sort of a monthly ET. And it's like, man, when OpenET became available, it's like, why don't we just flip that all around and drive ET into this model with actual observations of ET? And the beauty of that is that it sort of intrinsically integrates the crop planting dates, right? You don't need to know information about when the crop was planted. It's sort of embedded in your observation of the energy balances from remote sensing. You don't need to know so much about water availability and when that water became available for flooding a rice field or not. If there's changes in cultural practices, maybe they're drawing the field down and then applying an herbicide and then drawing it back up that you wouldn't know about in your static understanding of land use, but using remote sensing, it's integrated into your product basically. So this is a really exciting space, I think, to drive these data into our hydrologic models. And then finally, this is one that's exciting for like a rapid assessment of groundwater extraction. I think some of our colleagues here are going to talk about this from DRI. But basically, we're using OpenET data together with PRISM precipitation data to basically come up with this thing that we're calling groundwater extraction estimates from Earth observations, or GEO. And it's just a rapid assessment of groundwater extractions primarily for groundwater sustainability plan reports. And basically, there's all sorts of benefits from that, but I'm gonna skip that and just kind of get to a quick kind of a schematization. So we're basically just doing pixel scale water budgets. So if you kind of look through the green water part that Gabriel teed up nicely, you look at the blue water part, that's the applied water piece, And if you have a measurement of your applied surface water, you can basically do this pixel scale water budget and kind of back into what your applied groundwater must have been. There's some other flow paths that we're making some assumptions and estimates and hopefully measurements of, ideally, to back into that pixel scale applied groundwater value, and then you can aggregate that to whatever spatial or temporal scale you want. So it's a really elegant approach, and credit to WIM and some stuff that we published on this in terms of this pixel scale water budget. Okay, 2 minutes for wetlands here. So we looked at 6 wetlands. This was a project with Point Blue, Audubon, and the Wildlife Conservation Board. The blue wetlands are what we're going to take a closer look at: Kern, Pixley, Mendota, Grasslands, Sacramento, and Butte. Basically, what we did was we looked at OpenET, ETA, and this is expressed in inches per month for across the series of 5 years from 18, 19, 20, 21, and 22, and for these 6 different wildlife areas. And I'll try to keep them in the same order. It's just alphabetical order. So right away, just from looking at ET, you can say that not all wetlands are the same. Of course, we know that because of water availability, because of energy availability, because of management on the landscape. But we then divided all those values by spatial CIMMUS reference ET in order to get what we're calling a habitat coefficient. It's just an evaporative fraction, so it's just the ETA over the ETO. And basically, the punchline of this work was these groups, the Audubon and Point Blue, were using a model called the Wetland Water Balance Tool, which had this kind of assumed habitat coefficient, which is shown in the gray lines here. And that basically was then being used across the different wetlands in California to make management decisions. And we just started asking the questions like, well, this was developed for the Sacramento National Wildlife Refuge, so you see pretty good agreement between the habitat coefficient there. But what about if you're down in Pixley? Does that same habitat coefficient represent the on-the-ground landscape and what's happening there? And I think the answer, of course, is not so much. I mean, they're water limited, and we'll see that here a little bit more in a second. So here's kind of just a closer view of what I just talked over again, and what we're looking at is the agreement between the actual habitat coefficient, or this evaporative fraction, and then the one that's being used in this current model. And really, just the things to highlight is that there's significant disagreement in the shoulder months and significant agreement in certain areas within the summer months. But then in other areas, that are water limited, there's really not agreement at any point in time. Kind of here's the spatial picture of ET across the Sacramento National Wildlife Refuge. This is the resulting habitat coefficient. Expressed from 0 to 1 here. So you see the extreme spatial variability. Here's like a permanent water body where it's pretty persistently around 1. Makes sense. Here's kind of a drier upland area where it's kind of on the order of 0.1 or 2, quite a bit drier. And then this will be kind of the last, I think, technical slide here. This is just a deviation from what the tool is using for habitat coefficients and the actual observed habitat coefficients over space and time. So you see that the blue means that the model is overestimating ET, and the red meaning it's underestimating ET. And we're kind of both high and low across space and time. And one way to kind of aggregate that is to sort of make a heat map where you can kind of see for each wetland how this habitat coefficient evolves over time, and see stuff like, boy, this one's water limited here, or boy, this one seems to have a real bias in the winter months there. So there's just a couple things to point out. All right. This is it. We're really excited about ongoing, highly accurate and accessible ground observations for this OpenET project. So, and that includes, I think, applied water, like some of the slides that I showed. We're excited to partner with the team on that analysis. I'm going to skip down to this last point, which is, and it's already been touched on in the plenary here, but the ongoing refinements to methods for estimating effective precip for computing ETAW. I mean, just in my world, that is like the holy grail that we're trying to, figure out, is how to get to that ETAW. And it's something, Gabriel, that you've already talked about as well. And it's just so important. So I'm really excited as a community to come together and continue working on that. Thank you for your time.
Thank you, Jeff. That's a really impressive portfolio of work, and I'm sure there's a lot to unpack during the Q&A session.